Welcome back. In this class we will solve Lagrange's linear equations of the first order using the method of multipliers, a combination of multipliers and a grouping method. Consider the question. Solve y minus z into p plus z minus x q is equal to x minus y, and this problem is directly in Lagrange format, that is capital P into p plus q into q is equal to r. And after identifying this as Lagrange's linear equation, we can write the capital P as y minus z and capital Q as z minus x and capital R as x minus y, because that is in standard format. Now writing the subsidiary equations, Lagrange's subsidiary equations are dx by p is equal to dy by q is equal to dz by r. That is dx by p means y minus z, dy by z minus x equal to dz by x minus y, and we call it as equation number 1. See, in this Lagrange subsidiary equations, we cannot apply the previous grouping method, because if we take the first and second ratio, we cannot exclude the third variable, say z. And similarly for second and third ratio, or if we take first and third ratio. So in this case, we will apply another method called method of multipliers. So here we can choose a proper multiplier so that suppose we are forming a fourth ratio in which the denominator is 0. Here we can properly choose the multipliers as 1, 1, 1. That means we are multiplying all numerators with 1 and denominators with 1, and suppose we are adding together all these expressions. That is, each ratios of the expression 1 is equivalent to dx plus dy plus dz divided by y minus z plus z minus x plus x minus y. That means from the three ratios we are forming a fourth ratio, and that fourth ratio with the denominator, what is the denominator? Y minus z plus z minus x plus x minus y, and on addition we can say that this part goes to 0. So this is equivalent to dx plus dy plus dz by 0. And whenever this denominator part goes to 0, we can have the numerator is also 0. That is dx plus dy plus dz is also 0. That is the numerator dx plus dy plus dz is also 0. That is in a direct integral format, or we can write this as d of x plus y plus z is equal to 0. Integrating we get x plus y plus z equal to a constant, that is u is equal to x plus y plus z equal to a constant. We call it as equation number 2. So we have obtained one solution as u is a constant, where u is x plus y plus z. Next we can have another set of multipliers. Suppose we are choosing the multipliers as x, y, z, and multiplying first with the x, second with the y, and third with the z, and adding together we get a fourth ratio as x dx plus y dy plus z dz, with the denominator x into y minus z plus y into z minus x plus z into x minus y, and on addition we can see that in the fourth ratio denominator part also goes to 0. Okay, now choosing another set of multipliers. Choosing the multipliers x, y, z, that is each ratios of equation number 1 is equal to x dx plus y dy plus z dz divided by x into y minus z plus y into z minus x plus z into x minus y. Suppose we are expanding the denominator of the fourth ratio, we get xy minus xz plus yz minus xy plus zx minus zy. On addition, we can see that this denominator part goes to 0. That is equal to x dx plus y dy plus z dz by 0. Hence, we can have the numerator x dx plus y dy plus z dz equal to 0. That is an integrable format. On integration, we get integral x dx plus integral y dy plus integral z dz is a constant. We call it as constant, say b. Or this one integration will give x square by 2 plus y square by 2 plus z square by 2 is equal to b, or x square plus y square plus z square is equal to 2b. That is, our v is equal to x square plus y square plus z square. That is a constant. Question number 3. That is, v is equal to x square plus y square plus z square equal to a constant called 2b. Question number 3. So we have two independent solutions. U is a constant and v is a constant. Hence, the general solution is f of uv is equal to 0, where f is an arbitrary function. That is, f of x plus y plus z comma x square plus y square plus z square equal to 0, where this f is an arbitrary function. See the second question. Solve x into y square minus z square p plus y into z square minus s square q is equal to z into x square minus y square. So writing the Lagrange subsidiary equations, the subsidiary equations are dx by p is equal to dy by q is equal to dz by r. That is, dx by x into y square minus z square dy by y into z square minus x square equal to dz by z into x square minus y square. We call the subsidiary equations as set number 1. As before, here also we cannot apply the grouping method because we cannot separate the third variable from any two pair of ratios. So we are looking for proper multipliers so that if you are forming a fourth ratio, its denominator becomes 0. So what is the choice for multiplier? Here we choose the multipliers as, suppose we are multiplying each of the expressions, first expression with the x, second with the y, and third with the z, and adding together, we get in the denominator of the fourth ratio as x square into y square minus z square plus y square into z square minus x square plus z square into x square minus y square, and on addition we can see that all these denominators goes to 0. Choose the multipliers as x, y and z, and each ratios of equation number 1 is equal to x dx plus y dy plus z dz divided by x square into y square minus z square plus y square into z square minus x square plus z square into x square minus y square. And on expansion and adding, we can see that the denominator of the fourth ratio becomes 0. So this is equal to x dx plus y dy plus z dz by 0. Hence, the numerator also goes to 0. X dx plus y dy plus z dz is equal to 0. That is an integrable format. Integrating, we get integral x dx plus integral y dy plus integral z dz is a constant, or x square by 2 plus y square by 2 plus z square by 2 equal to a. That implies u is equal to x square plus y square plus z square is equal to an arbitrary constant, say 2a. We call it as equation number 2. So this is the first solution. U is a constant. And similarly we can form another set of multipliers. What is a proper multiplier, so that the denominator of the fourth ratio becomes 0. Suppose we are removing this x, y, z from each of the denominator and adding. What happens? Y square minus z square plus z square minus s square plus x square minus y square, that becomes 0. So we can choose the multipliers as, in order to remove this x from denominator, we have to multiply this denominator with 1 by x. So the next set of multipliers are 1 by x, 1 by y, 1 by z. Then numerator becomes 1 by x dx plus 1 by y dy plus 1 by z dz by 0. Now we are choosing another set of multipliers as 1 by x, 1 by y, 1 by z. We can write each ratios of equation 1 is equal to 1 by x dx plus 1 by y dy plus 1 by z dz by removing that x, y, z by multiplication with 1 by x. So we get y square minus z square plus z square minus s square plus s square minus y square, and this on addition will give the answer 0. That is 1 by x dx plus 1 by y dy plus 1 by z dz divided by 0. Hence the numerator 1 by x dx plus 1 by y dy plus 1 by z dz also 0. Integrable format, again integrating we get integral 1 by x dx plus integral 1 by y dy plus integral 1 by z dz is equal to some constant. Here we can choose the constant properly as logarithm, because each of the integral will give the logarithmic answer. So we call it as log b. That is integral 1 by x dx, that is log x plus log y plus log z is equal to log b, or log of, this implies log of xyz is equal to log b, or xyz equal to b. That is v is equal to xyz, v is equal to xyz equal to b. We call it as equation number 3. So we have two sets of solution. First solution was x square plus y square plus z square is a constant, and another v is equal to xyz is a constant. From equations 2 and 3, the general solution is an arbitrary function of u comma v is equal to 0. That is f of x square plus y square plus z square comma xyz equal to 0, where this f is an arbitrary function. Or we can modify this solution in the form xyz equal to an arbitrary function phi of x square plus y square plus z square. This is an alternative form of representing the same family of solution in terms of arbitrary function. See the third problem. Solve mz minus ny into dou z by dou x plus nx minus lz into dou z by dou y equal to ly minus mx. Here instead of the notations p and q, we have used the direct symbol dou z by dou x and dou z by dou y, and it is understood that here this L, M, N are constants, and here the variables are x, y, z. So this is in direct Lagrange form, p into p plus q into q is equal to r. So we are directly writing the subsidiary equations. The subsidiary equations are dx by p. What is p? Here p is mz minus ny is equal to dy by q nx minus lz equal to dz by ly minus mx. Question number 1. So here also we cannot apply the grouping method. So we are looking for proper multipliers, so that in the fourth ratio denominator becomes 0. Any guess what are the proper multipliers? Suppose we are multiplying each of the expressions with x, y and z and adding. Then we will see what happens. Choose the multipliers. Choose the multipliers as x, y, z. Then each ratios of equation number 1 is equal to a fourth ratio x dx plus y dy plus z dz divided by x into mz minus ny plus y into nx minus lz plus z into ly minus mx. Suppose we are adding the denominators of the fourth ratio. X into mz minus ny plus y into nx minus lz plus z into ly minus mx. This on expansion we can see that this goes to 0. That is x dx plus y dy plus z dz by 0, because for every term there is a corresponding negative term. Hence the numerator part x dx plus y dy plus z dz is also 0. Integrable format, on integration we get integral x dx plus integral y dy plus integral z dz is equal to some constant a, or x square by 2 plus y square by 2 plus z square by 2 is equal to a, or this implies x square plus y square plus z square is a constant, say 2a, that is u is equal to x square plus y square plus z square equal to a constant 2a, equation number 2. And similarly we can construct another solution, say b, by properly choosing another set of multipliers. What are the multipliers? Suppose we are choosing another set of multipliers as, instead of x, y, z, suppose we are taking it as L, M, N. Then in the fourth ratio the denominator becomes L into mz minus ny plus m into nx minus lz plus n into ly minus mx. On expansion again we can see that in the fourth ratio denominator becomes 0. Choosing the second set of multipliers as LMN, we get the fourth ratio with the numerator LDX plus MDY plus NDZ and denominator L into MZ minus NY plus M into NX minus LZ plus N into LY minus MX. And this on expansion we will get the answer as 0 in the denominator, because we have a positive term LMZ minus LMZ get cancels, Ln minus Lny plus Lny equal to 0, and similarly for the another term. So this is equal to LDX plus MDY plus NDZ by 0. Hence, we have the numerator quantity LDX plus MDY plus NDZ also 0. On integration, we will get integral LDX plus integral MDY plus integral NDZ is equal to some constant AB, or Lx plus My plus Nz is equal to B. That is, this is our second set of solution, say B. That is, V is equal to Lx plus My plus Nz equal to B, equation number 3. And from equations 2 and 3, we can have the general solution. Hence, the general solution is an arbitrary function of uv is equal to 0, that is f of, what is our u? U is x square plus y square plus z square, comma, Lx plus My plus Nz, this is equal to 0, where this f is an arbitrary function. Next we consider another different problem. Solve y plus zp plus x plus zq is equal to x plus y. Clearly this is in direct Lagrange form, pp plus qq is equal to r, and if you are writing the subsidiary equations are dx by p, that is ds by y plus z is equal to dy by x plus z is equal to dz by x plus y. Set number 1. For solving this problem, here we are going to construct another 3 ratios using 3 sets of proper multipliers. Suppose we are choosing the multipliers as choosing multipliers as one set is 1 1 1 and another set is 1 minus 1 0 and the third set of multiplier is 0 1 minus 1. So each ratios of case number 1 is equivalent to, for the first set multiplier 1 1 1, that means we are multiplying every ratio with 1 each and adding together, we get a fourth ratio as dx plus dy plus dz. Dx plus dy plus dz divided by y plus z plus x plus z plus x plus y. It is a sum. Every term is repeating, that is 2 into x plus y plus z is equal to, and fifth ratio, for the fifth ratio the multipliers are 1 minus 1 0. That means we are multiplying first with 1, second with minus 1 and third with 0 and adding, that means dx minus dy. So this is dx minus dy divided by then y plus z minus of x plus z. What is y plus z minus of x plus z? That is y minus x, or it is minus of x minus y. Okay, is equal to, for the third set multiplier 0 1 minus 1, multiplying first with 0, second with 1 and third with minus 1 and adding. So we get dy minus dz by this part becomes 0, x plus z minus of x plus y. So x get cancels, so we have z minus y, or it is minus of y minus z. So this is a different pattern. In the same set we are choosing 3 sets of multipliers and constructing 3 more ratios. Okay, and now these ratios are in integrable format. That means the numerator of the fourth ratio, this can be written as d of x plus y plus z by x plus y plus z, and this is d of x minus y divided by minus of x minus y, and this is d of y minus z by minus of y minus z. That means from the constructed 3 ratios we can have 2 sets of grouping, and that will suggest 2 independent solutions. That is a method. From the fourth and fifth ratios, we have d of x plus y plus z divided by 2 into x plus y plus z is equal to d of x minus y divided by minus of x minus y. That is in a direct integrable format. Suppose this x plus y plus z is equal to t, then it is dt by 2t form, and this is some let us say s, then ds by minus s form. On integration, integrating we get integral of d of x plus y plus z by x plus y plus z. We can remove the constant 1 by 2 outside, is equal to minus of d of x minus y divided by x minus y plus some constant. Here we can expect the answers as logarithm, so we properly take the constant of integration as log a. Okay, that is, after integration we get, this is, what is integral of d of x plus y plus z by x plus y plus z. Suppose we are replacing this x plus y plus z as t, then it is dt by t, integral dt by t, that is log t, or we can write this as log of x plus y plus z is equal to minus log of x minus y plus log e. Collecting logarithms, that is this is log of x plus y plus z raised to 1 by 2 and adding, that is plus log of x minus y becomes multiplication, that is into x minus y is equal to log a. Now taking anti-logarithm on both sides, we have x plus y plus z raised to 1 by 2, or this is square root of x plus y plus z into x minus y is equal to a. We call it as another set number 2. That is, we get a solution as u is equal to root of x plus y plus z into x minus y equal to a. This is our equation number 2. And similarly, we can construct another set, say v is a constant from the remaining ratios. Suppose we are looking at the fifth and sixth ratios, that will suggest another independent solution. From the fifth and sixth ratios, we have d of x minus y divided by x minus y is equal to d of y minus z divided by y minus z, because that negative sign in the denominator is a common factor. So we are cancelling that. So d of x minus y by x minus y is equal to d of y minus z by y minus z. That is a direct integral format. So this one integration will give integral d of x minus y by x minus y is equal to integral d of y minus z by y minus z plus log b. So that is this is log x minus y is equal to log y minus z plus log b, or we can collect the logarithms to the left hand side. So this is equal to log of x minus y divided by y minus z is equal to log b. Taking anti-logarithm on both sides, we have x minus y divided by y minus z is equal to b, or v is equal to x minus y divided by y minus z is a constant. Set number 3. So we have two independent solutions, hence the general solution is f of uv is equal to 0. That is f of first expression square root of x plus y plus z into x minus y, comma x minus y divided by y minus z equal to 0, where this f is an arbitrary function. Okay, thank you.